Hey guys, sorry I'm not there today. Sick at home, so I figured I'd record this video and then at least you have something to go over. Today we should probably be able to finish the rest of our midterm review. So we're going to look at calculating probability, then we'll do mutually exclusive and independent events. It should go decently quick, and then you'll have time to work on a practice booklet that I've left for you guys. It should get handed out. If you don't want to do those questions, you could also go back to your textbook and start practicing in there because there's always lots and lots of questions in that textbook. So you can do either or both. Tomorrow, you guys are going to have a practice box so you guys can work on, again, the textbook or the practice problems together. And then on Thursday will be your midterm. Remember that the midterm is a replacement exam for your first two units. So if you're hoping to reassess, that's your opportunity to reassess. All right. Calculating probability. So this is like the mathematical formula for calculating probability right here. But we don't actually use that. Typically, we just break that down into more simpler terms. And we say that probability equals what you want divided by what was possible. And it's really like how many things you want divided by how many things were possible, right? But we just say want and possible. We've done way harder probability questions in Unit 2. So Unit 1 questions should actually be much easier now that you're looking back at them. So we look at question number 1. It says a fair die is rolled. What is the probability of rolling a 6? A fair die has 6 sides. Sorry. So if we think about this, we would say what is the probability of rolling a 6? What we want is a 6, and there's one way of getting that. What's possible when you roll a dice is any of the 6 numbers. So our probability of rolling a 6 equals 1 over 6. Awesome. Question 2. A card is drawn from a standard deck of cards. What is the probability of drawing a heart or a club? So we are looking at what we want and what's possible because it's a probability question. What we want is we want a heart or a club. So for us, we know there's 13 hearts and 13 clubs. That makes for 26 things that we want. We'd be happy with any of those 26 cards. What's possible when you have a deck of cards is any of the 52 cards get drawn. Probability equals want over possible. That's 26 over 52, which is 1 over 2. You could also express that as a decimal, right? So if you calculate 1 over 2, you would get 0.5. Wonderful. Number 3. A card is drawn from a standard deck and then replaced before another card is drawn. What is the probability of drawing a heart and then a club? Okay. When we see and, that tells us that we want to multiply probabilities. So what we really want to do here is we want to do the probability of drawing a heart, then multiply it by the probability of drawing a club. And it is important to note that the card is replaced, right? So they always kind of give you that keyword somewhere in there. It's either replaced or not replaced. If it's replaced, we need to consider that. So, tackling this question, what is the probability of drawing a heart and then a club? The probability of drawing a heart would be there's 13 hearts divided by there's 52 possible cards. And means we're going to multiply these probabilities together. Then you draw a club. There's 13 clubs. And because we replaced that original card, it's still out of 52. So the probability of drawing a heart and then a club would be 13 out of 52 times 13 out of 52. If you put that in your calculator, you should get as a fraction, I believe it's 1 out of 16. Let me go grab a calculator and make sure. Yeah, so it was 1 out of 16. As a decimal, when we multiply those together, it was 0.0625. Right, both of those answers are correct. So this is the fraction answer, and this would be the decimal answer. Your calculators, remember, can convert decimals to fractions by hitting math and then frac, and it'll convert it over for you. So when we did probability, in the last unit, the probability questions were much harder, right? We had to do perms and coms on the top and perms and coms on the bottom. When you have a simplistic situation like this where you're just having one thing happen, right? I drew one card, right? And then I drew another card, like very simplistic things. It's sometimes easier to calculate it the way we just did right now, where you don't actually have to even do perms and coms. You still could do perms and coms on questions like this. So for instance, if I wanted to do this question, but with perms and coms, for the blue side, I would say there's 13 hearts, choose one of them, divided by there's 52 cards, choose one of them. And these two things are equal, like they're equivalent. One's just us kind of thinking about it, right? The top is like, well, how many hearts are there? There's 13. Okay, awesome. And the second way is us using perms and coms and understanding I can do 13, choose one to draw that one card out. So if you're still wanting to do it this way, which is the way we learned in Unit 2 and the way you had to do in Unit 2, then that's fine. You can do that for Unit 1 as well. If you want to break it down to a more simplistic manner like this way, then that's fine as well. Just to finish off what that would look like as a perms and coms, I would then go multiply by, and I would do 13 clubs, choose one, divided by 52 cards, choose one. Awesome. Complementary events. We talked about this a bit yesterday. Complementary events are opposite events, right? So the opposite of rolling a 6 is not rolling a 6. The opposite of being in English is not being in English. The opposite of passing math class is failing math class. Right? Complements are opposites. The thing with probabilities and complements is that when you add two events that are complements together, it should equal 1, because that means there's a 100% chance of it happening, which makes sense, because if we add a probability of something happening to the probability of it not happening, the opposite, then one of those two things should be guaranteed to happen. Right? Like, that only kind of makes sense. If you think about, if you add the probability of passing math plus the probability of failing math, like one of those two things has to happen. So that should equal 1. This question is talking about what is the probability of rolling a 6 and not rolling a 6. Probability of not rolling a 6 would be there's 5 things out of 6. Probability of rolling a 6 is 1 out of 6. These are complementary events, meaning they're opposites, right? Rolling a 6, the opposite is not rolling a 6. Because they're complements, if you add them together, they should equal 1. And if you try it, they do, right? You go 5 out of 6 plus 1 out of 6, and it does equal 1. We use complementary events a lot in Unit 2, right? It saves us doing lots of calculations. Wonderful. Odds. Odds were another way of describing probability, right? So if we think about probability as the chance of something happening, like that's what it's telling us, the likelihood that something will happen. Odds is doing the same thing. It's telling us the likelihood of something happening, but instead of giving it to us in a fraction or decimal form, it gives it to us in a comparison of numbers. Okay, so if we look at this question, it says what's the probability of rolling a 6 on a 4 on a 6-sided dice? There's 1 4 divided by 6. That would be the probability. If I wanted to do the odds of rolling a 4, or the odds for rolling a 4, the odds of, or the odds for, are 1 to 5. And what that 1 to 5 is telling us is that there's one thing we want versus 5 things we don't want. Where probability told me that there's one thing I want, and then divided by what's possible. So odds actually uses the complement, right? It's telling you the number that you want to have happen and then the opposite, what you don't want to have happen. They also do odds against. Odds against is the same as odds for, but in reverse order. So if odds for were 1 to 5, the odds against would be 5 to 1. So that would be don't want comes first versus do want second. Again, it's just a different way of telling me the likelihood of something happening. Sorry if I keep coughing and sneezing in your ears. It's probably getting annoying. Awesome. So at the bottom here, we got like two little formulas. That's the mathy way to write them out. I like to have my own way. So odds in favor of. So odds in favor of, we usually call it odds for. The way we write that is we write what we want as the first number. Then we do a colon. And then we write how many things we don't want. When we're doing odds against, we reverse those numbers. It's don't want versus do want. Wonderful. That's odds. If you look at a question of odds right here, typically we see odds in gambling and sports. So this one is Las Vegas is a common place to use odds. Recently, they released the following odds against each NHL team winning the Stanley Cup. So odds against team winning the Stanley Cup. So that means they're doing don't want, which would be not winning the Stanley Cup, versus do want, which is wanting to win the Stanley Cup. So when you're reading these numbers, let's look at Pittsburgh Penguins. The Pittsburgh Penguins say that for every 9 times they lose, there's 1 time they win. For the Edmonton Oilers, if we're looking at this, that means for every 10 times they lose, there's 1 time that they do win the cup. And so on and so forth. So if you're looking and you're trying to compare odds, typically comparing odds is hard if the numbers are different. Comparing odds is really easy if the second number is the same, or even if the first numbers are all the same. But if you look, all the second numbers are 1. That means it's easy for me to compare these odds. Because every single one of these this is how many times I lose versus 1 time that I win. So for Pittsburgh, they lose 9 times to win 1. Edmonton loses 10 times to win 1. Washington loses 10 times to win 1. Anaheim loses 14 times just to win 1. Toronto loses 16 just to win 1. Dallas 20 to 1. In Calgary, obviously, last place, they lose 33 times before they win 1. We're actually getting pretty close to that. Last Stanley Cup they won was 1989, so that's been about 31-ish years. So it's getting close. Maybe Flames fans, you have a chance of winning again. So if you look at question A, which team is most likely to win the Stanley Cup? That would be Pittsburgh, according to this question. The reason why is because they only had to lose 9 times to win it once. That's the least amount of losses compared to everybody else. B, which team is least likely to win the Stanley Cup? That would be our good friends to the south, Calgary. They lose an amazing 33 times before they win once. C, what is the probability of the Oilers winning the Cup? And that's a great question because we have to now somehow go from odds, which is 10 to 1. We got to convert that into probability. Think about what odds is telling you. This was odds against. So that was telling me there's 10 things that I don't want. And there was 1 thing that I do want. Probability equals what you want divided by what's possible. Well, one of these numbers is going to be easy. What I want is in common. So it's pretty easy for me to say, all right, my probability on the top is going to be 1. Because that number's in common, right? I got it right from my odds. But in my odds, nowhere does it have a possible value. It has a don't want and a want value. If you want to figure out what's possible, then you need to add those things together. If you do what you don't want plus what you do want, that will give you what's possible. So for us, it would be 10 things we don't want plus 1 thing we do want gives us 11 possible things. 1 out of 11 would be the probability of the Oilers winning the Stanley Cup. Typically, the reason we convert from odds to probability is when the odds are all different and crazy numbers, and we're trying to figure out what's more likely to happen. Probability is easy to tell what's more likely to happen because you can just turn it into a decimal and then figure out which decimal is the highest. And this decimal is 0.09. Any number smaller than that has less probability. Any number bigger than that has more probability. All right. That's odds. We're going to get into a couple definitions here. The first definition is mutually exclusive events. Mutually exclusive is a term we use to date people, right? We say 2 people are mutually exclusive. It means that they can't date other people at the same time. They're just the 2 of them dating. Mutually exclusive in probability also means the same thing. Mutually exclusive means 2 things can't happen at the same time. Just like dating, right? Mutually exclusive means 2 people can't date other people at the same time. In math, mutually exclusive means 2 things can't occur at the same time. So for instance, if I have a deck of cards and I want to draw a red card out of the deck, so I go and I draw a card. It is not possible for me to draw a red card and draw a spade at the same time because I either got a red card or a spade or something else. I could have got a club as well, right? But it's not possible that I draw a red card that's also a spade. Not possible. So those are mutually exclusive events. This means that mutually exclusive events should have nothing in their Venn diagram when you look at the A and B. It should equal an empty set. There should be nothing in there. Because there's no way that both those things happen at the same time. Wonderful. If 2 things can't occur at the same time, we also get a rule that the probability of those 2 things happening at the same time equals 0. Right? If they can't happen at the same time, there's no probability of them happening at the same time. Cool. If 2 things are possible to happen at the same time, even if they're really, really unlikely things to happen at the same time, then we would say they are not mutually exclusive events. So even if it's super rare, it's still called not mutually exclusive if there's any chance of it happening. Independent events. Independent events are events that do not affect each other's outcome. So for instance, if I roll a dice and I spin a wheel, those 2 events don't affect each other. If I roll a 1 on my dice, it doesn't affect what I'm going to get on my wheel. So independent events, I'm going to say 2 events that don't affect each other's probability. An example of this, how independent and dependent events can change, is this first example says 1 card is drawn from a deck of standard cards and then is replaced. A second card is then drawn from that deck of cards. Question A, or event A, is the card is a heart. So if we think about the probability of drawing a heart, there's 13 hearts, and then you divide by 52. Event B is that the second card is a heart. Well, after I drew out the first card, I then replaced it, and then I drew another card. So there should still be 13 cards in the deck, and there should be 52 cards still total. However, if we look at the second part, the second example right here says the card is not replaced. So when we consider our probabilities, A, the first card is a heart, would be 13 out of 52. Now when we go to do the second card as a heart, there's two different situations. Situation 1 is there's only 12 hearts left. Right? So situation 1 is, oh, you took a heart out, now there's only 12 left. Situation 2 is that you missed and you didn't get a heart. Therefore, there's still 13 hearts left in the deck. But because I never replaced whatever I took out the first time, I now have two different situations. There is 12 hearts left, meaning there's 12 out of 51 remaining cards, right? Because there's one less card now. Or there's 13 hearts left out of 51 total cards. Either way, event A has had some sort of effect on event B happening. If event A did happen, my probability got lower for drawing a second heart. If event A didn't happen, if the first card wasn't a heart, then the second card actually becomes more likely. The probability got higher because now there's less other cards to draw from. So I have 13 out of 51 rather than this 13 out of 52 up here where I replace the card. Example A was independent events because I replaced the card. And it didn't matter what happened on the first event because I replaced it and then I redid the thing. The second example is an example of dependent events because depending on what happened in the first situation, the second situation changes and it alters compared to if the first situation hadn't happened. That's independent events. On your formula sheets, there's some formulas for mutually exclusive and independent events. Okay, these formulas are all right here. The mutually exclusive event says that the probability of A or B happening equals probability of A plus the probability of B. Non-mutually exclusive events say that when you do the probability of A or B, you can still add A and B, you just have to subtract their overlap. So subtract the probability that both things happen. The next one is our dependent formula. This is the probability of A and B equals the probability of A times, and then that symbol is new to us. The way we read that is the probability of B given A happened. So for instance, if you look back up here, this example, this would be the probability of B given A happened, right? That's the probability of drawing another heart given that the first card was a heart. This probability over here, this is the probability of B given A didn't happen. Right? That's the probability that you draw a second heart given that the first event didn't happen. So when we go down here, our formula uses that notation. This is the probability of A and B equals the probability of A times the probability of B given A happened. If two events are independent, we just do the probability of A and B equals the probability of A times the probability of B. We did have kind of an unwritten rule that worked most of the time. And that unwritten rule was when you're doing or. So if you're doing probably something or this, it means to add. We've been doing that lots in Unit 2, right? Every time we saw or, it meant we were adding events together. The second part, this, gives us a unwritten rule that when you read the word and, it means you're going to multiply. So when you're reading probability questions, if you are being asked to find the probability of this or this, then you need to add the probabilities together. If you're getting the probability of this and this, it means you're going to multiply probabilities together. Then you got to decide if you need to subtract away something or change the second probability because it depends on the first one. Like, it can get a little bit more tricky, but that's our general rule. Or means add, and means multiply. Awesome. Let's see a couple questions. We'll jump down to the bottom here. It says, if, down here, if P of A, so that's the probability of event A, equals 1/3, P of B, probability equals 2/5, and the probability of A or B is 3/5, investigate whether A and B are mutually exclusive or independent. Now, typically when I'm asked, is something mutually exclusive, is something independent, then I just use context and I think about it. And I'm like, oh yeah, okay, the probability of passing math and winning my soccer game, those are non-mutually exclusive. Both those things can happen at the same time. But in this case, there's no context. This means you have no idea what event A is. You have no idea what event B is. So you can't really make a decision on these events being mutually exclusive or not by thinking about it and considering the context. So instead, when you have no context, that tells you need to check your formulas and you need to test them. Our mutually exclusive formula, if we look back up here, our mutually exclusive formula tells us that the probability of A or B should equal the probability of A plus the probability of B. So we're going to test that. We're going to say the probability of A or B should equal the probability of A plus the probability of B. If that formula works, then you have mutually exclusive events. If that formula doesn't work, then you don't have mutually exclusive events. Let's plug our numbers into our formula. So probability of A or B is 3 out of 5. Equals the probability of A is 1/3 plus the probability of B, which is 2/5. If you put that in your calculator, 3 divided by 5, it gives you 0.6 equals, and you do 1/3 plus 2/5, and you get 0.73 repeated. Notice that those numbers aren't the same. Therefore, the formula didn't work. Therefore, these are non-mutually exclusive. And I just proved it. I just justified my answer. Awesome. The reason why the formula didn't work is because we had non-mutually exclusive formulas, which meant there was some overlap. There was a possibility of A and B happening, and we've double counted it. So when you have non-mutually exclusive formulas, this gap right here in between these two numbers is what happens when you have the probability of A and B. So for us, this means we can actually calculate something. We could say the probability of A and B equals 0.73 repeated minus 0.6, which means the probability of A and B equals 0.13 repeated. That little jump in logic that we just did right here, right there, we're going to need that to now test out this question on whether or not these events are independent or not. The reason why we're going to have to do that is because the independent formula, if you look up here, the independent formula requires the probability of A and B. So you actually had to use this little trick to figure out what the probability of A and B was, so that I can then use my formula, probability of A and B equals the probability of A times the probability of B. Wonderful. Let's test that theory. So probability of A and B was 0.13 repeated. It equals the probability of A, which is 1/3, times the probability of B, which is 2/5. If you put that in your calculator, 1/3 times 2/5, you get 0.13. Because that formula worked, these are independent events. And I have proven or justified my answer. Awesome. You might want to just rewind this video and rewatch that question again, because that question is typically a lot to handle. Okay, last one. Conditional probability. So that's using the A given B happened. This says let A and B be events. I'm going to underline the information. Probability of A equals 1/2. Probability of B equals 1/3. And the probability of A and B equals 1/4. Determine the probability of B given A happened. That's what this is saying. Okay. The only place we ever see this given formula, is up here. Right? This is the only spot I ever see it. So that means I somehow have to use that formula in this question. And that formula is the probability of A and B equals the probability of A times the probability of B given A. Awesome. If you look at this, because we're trying to solve for probability of B given A, we want to try to get this by itself. Right? The way we get that by itself is by dividing the probability of A to the other side. This gives us a new rearranged formula, which says the probability of A and B divided by the probability of A will equal the probability of B given A. So we took our formula, we rearranged our formula so that we got what we want by itself, and now we can start plugging in numbers. So we'll start with the top of that fraction. The top of that fraction is probability of A and B, which is 1/4. Then we want to divide that 1/4 by the probability of A, which is 1/2, so 1/2. And when we calculate that, it should tell us the probability of B given A. When you're putting this in your calculator, make sure you put brackets around your fractions. So I'm going bracket 1 divided by 4, then close the bracket. And then I divide by bracket 1 divided by 2, and I close the bracket again. If I do that, I get 0.5 is the probability of B happening given A happened. Awesome. Let's look at B. So B says the probability of A given B happened. So they've reversed it. So when you get that situation, your formula for dependent events needs to slightly change. Because now they're saying that the probability of B has happened. Therefore, probability of B has to be the first thing in your formula, as compared to before when it was probability of A in this spot. This was probability of A because A had happened. In this question, B happened. So therefore, we have to have probability of B instead of probability of A. And then we multiply that by the probability of A given B happened. Again, we're going to rearrange. So we're going to divide that probability of B to the other side. This gives us a new little formula. So we have the probability of A and B divided by the probability of B equals the probability of A and B. Again, you're just going to start plugging in your things. So probability of A and B is 1 over 4. Put that in brackets. Divide that by the probability of B. In this case, the probability of B is 1 over 3. As I see up here at the top, probability of B, 1 over 3. Close those brackets. And that equals the probability of A given B. So then in your calculator, 1 divided by 4, divided by 1 divided by 3, and we get 0.75. Is the probability of A happening given B happened. Awesome. The last question. The last question says the probability of A or B. Now, I know that the probability of A or B equals the probability of A plus the probability of B. Because or means add. Now, in this case, because there's a possibility that both of those things happen, I need to remember to subtract away the probability of A and B. So it's still adding. I did probability of A plus probability of B, but then I have to subtract away the probability that they both happen. It's called the overlap, right? Let's just plug some numbers in here. So it means probability of A or B equals the probability of A, which is 1 over 2, plus the probability of B, which is 1 over 3. Subtract the probability of both of them happening, it's 1 over 4. You throw that in your calculator. You're going to get a decimal first. So you're going to get 0.5 plus 1 over 3, and then minus 0.25. You get 583 repeated. You could turn that to a fraction by going math frac, which is 2 or 7 out of 12. That's the probability of A and B happening at the same time. Or sorry, A or B happening. Wicked. I know that was probably a pretty long video to listen to. You will have the rest of the class to practice, and you'll also have all day tomorrow to practice. Best of luck. Thank you very much. Hopefully I see you soon.